quotient rule, the order starts to matter. So again, I'm going to color code things. I've got one function on the top divided by another function on the bottom. And here the order matters. With the product rule, just keep one the same derivative of the second, keep the other one the same derivative of the first. Doesn't matter the order. But with the quotient rule, you have to keep your bottom one the same first, multiply by the derivative of the top one, then keep the top one the same, multiplied by the derivative of the bottom one. You subtract instead of add, which seems to make sense with quotient. Because like if you think about log laws, if you're multiplying, you add. If you're dividing, you subtract. It's sort of connected to that. You've seen this before, so that doesn't hurt your brain too much. Over, and then the bottom one stays the same, but it gets squared. This is crazy. This is nothing like what you started with, but it works out perfect. So the top one is sort of notation with Newton. The bottom one, we can do the same notation Leibniz. You would keep the bottom the same. Then this is Leibniz notation for the derivative of the top. Then keep the top one the same. Derivative of the bottom over the bottom one squared. I think your formula sheet is all Leibniz notation. Not formula sheet, formula book, because it's like big. Formula no. When does a booklet become a book? That thick, right? Simply stated. I think that's funny. Don't you like it? What was it? The derivative of the quotient is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all divided by the square of the denominator. Oh yeah, I get it now, Mr. Chair. Thanks for stating it so simply. I think the color coding is the way to remember the way things go. But I'm not sure this is so simply stated. I like to think of it as keep the bottom the same times the derivative of the top minus keep the top the same derivative of the bottom over the bottom. The bottom stays on the bottom and it gets squared. Okay. So, I'm going back to the other one. Here we go. Find the derivative. This is my function on the top. This is my function on the bottom. So the derivative will be, and again, I'm going to try to get you all these formulas are on your formula sheet, but if you have them memorized, then you can move through things a lot quicker, right? And if you're like unsure, did I memorize it right? Well, it's nice. You always have your formula sheet there to double check. So in this one, we're going to keep the bottom the same, okay? So that would be 3x minus 7. Then we multiply by the derivative of the top. That would be 3x squared minus, now keep the top the same, and multiply by the derivative of the bottom. All over the bottom squared. So here we've kept bottom the same. Here we have the derivative of the top. Then we keep the top the same. And here we have the derivative of the bottom. And on the bottom, it gets squared. Now, sometimes in university, they get you to prove these derivative rules. So that can sometimes be just a little bit different. Often what's scary in university is that a university professor, a mathematician, doesn't like to use something if it hasn't been proven first. So you might be in a university class and they're like, before we can use this fancy shortcut of a rule, I have to prove it for you. And for the student that hasn't taken calculus, the proof looks crazy and complicated and you get lost and you're like, I don't know what's going on. And they don't tell you that, oh, often the mathematician, I need to do this for myself because I'm a mathematician and I can't, in good conscience, teach you how to use a shortcut without showing you where it comes from. But after I show you the thing that you don't understand and don't get, feel free to use the shortcut all the time and not worry about the proof. But what happens is students go and they go like, I don't get this at all. And it's actually, you're going to be in university and go, you know what, it's not going to be that bad. You won't have to worry about it too much. It's going to be okay. But then sometimes they do ask you to prove them on exams, so you do have to kind of learn it. But for the most part, it's just, once we have the rule, we can use it as a shortcut. And if you think back, where were we when we began our derivatives? We were using our formula f of x plus h minus f of x over h in the limit and having to do all the algebra to simplify. Like, this wouldn't be fun to do. You'd have algebra with fractions and your simplification would take a long time and it would work out, but the shortcut is a lot better. Again, function on the top, function on the bottom. Nothing really simplifies. Sometimes you can simplify things and make your life easier, but nothing simplifies here. We'll do one more together. So, derivative would be keep the top the same, keep the bottom the same, multiply by the derivative of the top minus keep the top the same, multiply by the derivative of the bottom, over the bottom squared. If you hadn't already memorized the derivative rule for powers, how annoying would it be to keep looking back at your formula sheet for like, oh, how do I do the derivative of x squared? Formula sheet has x to the n. Oh, move the n out in front and have an n minus 1. Like, you're going to have these rules memorized because they're just going to make your life easier. Color coding this one. Can you see that I kept this one the same? Then I did the derivative of the top. Then I kept the top the same. And did the derivative of the bottom. And then kept the bottom the same. All right, try the next couple on your own. Plan is to get up to rule number 7 today. Okay, how do you do on the first one? Are you ready for the answer for this one yet or not yet? Some yes, yes, no, not quite. I did some simplification, but you could have plugged in the -1 right away. And you get a slope of 1. X to the 4. Anyways, very cool. While you're working on this one, I'll graph. I'm sure you all have the picture of the natural log of x divided by tan of x in your head. I'll let you find the derivative first. Find the derivative. Yeah, got it. You have to create the excitement in math class. I can't wait to see what this graph looks like. Make my day. How'd you do on the derivative? Technically, this notation on the left is not quite right, but we'll leave it for now. Probably should write dy dx, but then there's no y, so probably then have to define, notation problems. All right, ready? And we'll move the graph into the middle here. Is this what you imagined? It's like a whole bunch of backwards tan graphs, except at the beginning. What? Why did it get so weird? Just at the beginning. There are asymptotes. Definitely are asymptotes. Asymptotes. Nice. Now, imagine this big graph in your head. Okay, we got it? Let's try it. Bracket tan x times 1 over x minus natural log of x, bracket. Oh.
I've never heard the term, we're going to foil it. Like, what does that mean? He's going to foil it. And even if it's not math, they'd be like, y'all are stupid.
It's a good math English. All right. You ready for this graph? You've imagined it in your head, right? Here we go. Ooh. Oh, cool. Look at how it's going like. It looks like, oh, I love that. All right. It looks like a dinosaur. Perfect. That's on video. We I could just call that. It's probably known within the math community as the dinosaur graph, but because that's kind of cool looking graph. Anyways, those are all the derivatives and all the slopes of this function. Now, the IB question has something like proofs. You know how you get proofs in identities? They do their proofs like this. They say, here's some information, show that, and then they give you the answer. So you need to start from the natural log over x squared and then use what you know about derivatives and simplifying to simplify it so that in the end the derivative looks like that. So what could you do to start with? Well, you could do your quotient rule. So keep the bottom the same, derivative the top, minus keep the top the same, derivative the bottom, over the bottom squared. And now that you've got your derivative, you just need to manipulate it until it looks like this. Now you're just using algebra skills. Can you see that you have an x to the 4 on the bottom? So you could simplify that to x to 4. Do you see that the top, that'll just simplify to x minus 2x natural log of x over x to the 4. And sometimes in a show that question, they kind of give you hints of what you should do. I need to cancel out one of the x's on the bottom. If I'm going to cancel out one of the x's on the bottom, I would need to have an x on the top factored out so that I could cancel it out. So I look, and sure enough, there's a common factor of x in both. I factor that out, I cancel it, and happy face. Adding the nose to a happy face doesn't quite make it as happy, right? It just looks sad. It's scary? It's scary.
It looks like
It's like if you were afraid of clowns, that would be equivalent. This can get you.
it's like watching me like make a mistake, and then it's gonna just like.
Right?
I love the smiley faces.
But not this one.
No. In identities,
yeah.
we always just put smiley faces. Like when you like taught your class to do it, like you were like so like you did like dots and like
important.
We just put a smiley face as a word and scribbled it out of it.
I mean, if our other graph looked like a dinosaur, this smiley face to me looks like a polar bear. Can you see it?
I think it looks more like a brown bear.
A brown bear? No, it's a polar bear.
It looks like it'd be fuzzy.
No, it's white. I don't know where you get brown from.
No, because they just look more friendly. Like a brown bear, a polar bear, like it's like don't go up to a polar bear. But like the brown bear.
This is like the polar bear that's on Coca-Cola. It's friendly.
Okay.
All right. Do you have these review questions? You do. But we have a question I missed. Right? Where's my... Oh, well. I guess we'll skip the question. It's not hard. You could try it on your own. So do the 2 review questions. I like the second review question. Oh, my sound! Has it been black for a long time? Our whole discussion about dinosaurs, brown bears, polar bears, scary happy faces with noses. It's lost. You'll just have to be a memory. Ooh, this one. you're like, we need to find the derivative. We got the squared here. So what would you like to do with this? If you have these things like this, you could either use your favorite new verb, or use your product rule. Happen to use your favorite new verb, multiplied it out, FOILed it, and then your derivative is just your basic power rule. And our last question for the day. Do you recognize that function? What is it? Area of a circle. And if you find its derivative, do you recognize that function? What is the derivative of an area of a circle? The circumference. It is a little bit much, I know. Just because we're on, like, that's kind of crazy. Okay? Do you recognize that formula? That is the volume of a sphere. If you take its derivative, that's the formula for the surface area of a sphere. So crazy. So the derivative of area of a circle is the circumference of a circle. The derivative of the volume of a sphere is the surface area of a sphere. And the derivative of nothing is, this is the inside of a donut. Its derivative is